Right. Good day, ladies and gentlemen. Let's continue. The last time, I believe, I more or less finished by giving you exercise, and then because of the short time, I cut a little bit the exercise, but then now I realize that it was too. I do need more general statement in order to make some point. So let me. I'm with apologies to those who already solved the exercise. I make a modification of the exercise. So it now consists of two points. A is you take L naught to be 1/2 d mu phi squared, where phi is a component vector. Now I add a potential term, d of phi squared. Now phi is phi 1, phi n. All right, and v is arbitrary potential term. That's L naught. So you want to show that, because it's not really easy to derive that. So I just give you answer, and you, if you want to, you check it. It works. So the equation is solved. The equation for the flow of the Lagrangian is solved by this formula: v divided by 1 plus alpha v, a minus 1 over alpha twiddle. So the last time I just missed this potential term. So 1 over alpha twiddle, and then there is minus 1 plus square root of 1 minus 2 alpha twiddle x plus 4 alpha twiddle squared z. All right, and that's it. So x here is as before, d phi squared, and z is a determinant of d mu phi. All right, and alpha twiddle is our old friend. Alpha 1 plus alpha v. Okay, so it's rather simple. It was actually I put a little question mark here because it was brought by some attentive students that there might be an issue with the factor of 2 here, somewhere over here. So that would be also an opportunity to fix this issue. It doesn't change much. Well, except that it would make a wrong answer into a correct one. All right. Anyways, that's so the point B, the part B, which I suggest, the second part, is calculate. It's actually part of the part A, this calculation, T mu alpha, the energy momentum tensor at point alpha, and check that if v equals 0, then T alpha mu mu equals to minus alpha T-Tbar alpha. Such identity holds. All right, and if v is not equal to 0, there are corrections to this identity. All right. So the point which I want to make at this point is that V equal to 0 corresponds to deformed conformal field theory, because with V equals 0, it's conformal field theory, and then alpha is the only dimensional parameter in the theory, and therefore one expects that the scale transformation is just rescaling of parameter alpha, and this is this formalizing of this statement. And then if there is introducing V necessarily brings in some mass parameters to the theory, then of course it's more complicated than that. This statement.
Say if V would be marginal this time.
Well, it's classical theory at this point. But now V is just at this level. V is a function of scalar field. So scalar field is dimensionless in 2 dimensions, and so in order to make for the whole thing to make sense, you need to introduce some mass parameter over here, right? So there would be a scale, and so scale transformation wouldn't be alpha transformation. This statement is it's overwhelmingly plausible that it's brought up to quantum level. So it's nearly obvious that in deformed theory, if the original theory is CFT, then alpha flow is mapped to RG flow. In other words, if you have a CFT over here, and this is alpha flow, then as to say the RG, there is a RG flow which goes right along that. So it's as the curve, it's the same curve. The A sub alpha T-Tbar flow is the same curve as A sub L RG flow. It's just the way of parameterizing this curve. So you say alpha is equal to some alpha star e to the minus 2L, something like that, and that maps one curve to another. On the other hand, if it's not a CFT, and deformed theory A naught is not a CFT, then one expects corrections to the state. One expects correction. And I just want to say that it's a nearly trivial statement, but generally in quantum case proving this identity is complicated and generally not solved problem. It looks sort of miraculous. So what let me recapitulate now what we have done in terms of this Lagrangian L sub alpha. Basically, we considered mostly the Lagrangian without this V term and recovered generally Nambu-Gotta theory, which was really Nambu-Gotta at negative sign of the parameter alpha, and was a kind of more strange theory, or you could say it's a sort of Nambu area in some pseudo Euclidean space with minuses in the signature, and that for positive alpha, and that was not, as Euclidean field theory, it was not bounded from below. I want to stress that it doesn't mean that we have to take this theory and throw it into a wastebasket, because it might be very well meaningful and sensible as quantum mechanical theory. It is just a straightforward trick of defining path integral through weak rotation. Doesn't work. Or it's not clear how to make it work. Yes?
Gflow, which operator is that?
Gflow, this Gflow is flow downstairs, and so it starts, well, basically we have seen that it starts somewhere outside the theory space, but it ends at some point. If it is a fixed point, it ends along T-Tbar. That's the sort of why we call one of the reasons. Well, there are many flows which end along the T-Tbar, but that one is so let me repeat it again, because I we have been asked infinitely many times this question, that if the undeformed theory is CFT, then the T-Tbar flow is mapped to Gflow. If undeformed theory is not CFT, then it's different curve in the theory space. Okay? All right. So any questions here? Because I want to, now the statement about Euclidean theory stability for one sign of alpha and then stability for the other was based on particular example. And that seems to be more or less general statement, and I want to argue in favor of that, at least in the classical theory, in the classical limit. So it's possible, it turns out that it's possible to bring up very general arguments which don't depend on specific realization of conformal field theory. Okay, so the argument would concern with a general argument. Let me on stability. So there might be done a general analysis on the basis of two assumptions. Simplifying assumptions. One is that undeformed theory A naught is CFT. Some CFT with some central charge, Virasoro central charge C. Okay? And the second assumption is that C is very large. This is semi-classical limit. Because in this limit, the components of the energy momentum tensor, T mu nu, becomes a classical field. All right, it's because the classical field means that the field whose fluctuations are negligible as compared to expectation rate. So if since its fluctuations are small, it's there are a lot of simplifications. All right, let me deal with these two assumptions in turn. So this would be two assumptions, and let me consider implications, separate implications of one and another. So first, I discuss what entails the A naught equals to CFT. Okay, then I assume that general basic properties of two-dimensional CFT are known. Just to remind yourself notations, I just remind that in CFT, the trace of the energy momentum tensor can be chosen in such a way that its trace is equal to 0. Then in complex coordinates, then the energy momentum tensor has two components, and in complex coordinates we have two components, TZZ, which I denote T, and T-bar, which is T z bar z bar. Okay, these are two components. And the continuity equation then tells us that this one is depends. The continuity equation says that this one depends on Z only, the galomorphic field, and T bar is anti-galomorphic field. And these two fields basically define generators of conformal transformations. These operators, Virasoro generators Ln ln bar, where n is an integer, and if the first collection generates Virasoro algebra of left movers. Let me call it left Virasoro, and I denote it by this symbol. And this is another copy of Virasoro algebra, and I denote it, guess what, the same thing with bar. All right, so they both have the same central charge, so I consider the most simple, straightforward case. And the full symmetry algebra, then, conformal algebra, then is the direct sum of these two, because they act independently. And therefore, if I look at the space of fields, we can identify in this case the space of states with the space of local fields. The space of fields decomposes into irreducible representations of the Virasoro of the symmetry algebra. So the space of fields which I decided to denote F, it is sum of over F sub alpha. These are irreducible representations of Virasoro algebra, and because it's of this substructure, F alpha is direct product of irreducible representations of each component, and the index alpha can run finite values in minimal models, infinite countable set, or continuous set. For me, at this point, it doesn't matter. I think we are prepared to deal with each of these situations, but I will basically think in terms of discrete collection of representations. So these are this V alpha and correspondingly V alpha bar. V alpha is a reducible representation of Virasoro, and it has a lowest weight which I denote delta alpha. And similar with V alpha bar, same of Virasoro bar, and generally some lowest weight delta alpha bar. So in all cases, this is a lowest weight modular. So that, let's say, V sub alpha is a span. So there are some primary fields associated with this. Phi delta alpha bar. It is primary field. And V sub alpha is spanned by all negative generators phi delta alpha delta bar. And similarly for V bar, the other right moving representation with the L bars, replacing L's there. Any questions here? So this is most basic structure of the space of states or space of fields in generic conformal field theory. Just like I said, alpha can be discrete or continuous or whatever. But in all cases that I know, the one of these F alphas, there is a vacuum model for whose primary field phi has delta equals 0 and delta bar equals 0, and the primary field coincides with identity operator. So I will call this vacuum module, and the associated V naught with the weight 0 and irreducible representation is, in physical terms, it's spanned by identity operator and all composite fields built from T and its derivative. So it would involve T prime, like T prime prime, and T squared, and all more complicated polynomials in T and its derivatives, where prime denotes, this is golomorphic field, so prime is just dz T of z. And squares and the more complicated are some natural way regularized products. There is a standard way to do that in conformal field. Anyways, so that's what we have in general. So that if I look at the full space F naught, which is a tensor product of this times the same thing built from T-bar, I discover this way that my space F is furnished by all composite fields built from T and T-bar. All right, so I can multiply now T and T-bar and take derivatives and doing all that and so forth. So that's all composite fields. In particular, T-bar is one of the vectors in this space. I will probably forget to say that, but this space F naught constitutes a closed algebra with respect to operator product expansion, and this is important statement for many of my statements which I am going to do to make sense. All right. So now let me remove this and do a little bit notational preparations again. So let me remember that as each representation, this vacuum module splits into level subspaces according to the level of in terms of Virasoro grading. So I will call it V sub n, with V upper index n, so that the V sub 0 n are eigenspaces of the L naught operator with the obviously integer eigenvalues. All right. Now I will need actually V naught hat, which is a factor of V naught over L minus y D naught, so that the derivatives are excluded, total derivatives are excluded from this space. All right. So let me denote Vi n with I running from 1 to dimensionality of this V naught n hat. It's easily computable number, but I don't need it real explicit form. Basis. So this would be basis in V naught n hat. All right. Then in the full vacuum module is equipped with this. Can be dealt with using this basis. No, I don't know. I don't know what I do. I probably want to remove this exercise now, right? Because I'm sure everyone already know how unsolvable the problem is. All right. My basis in this space F vacuum is going to be VI hat. No, V vacuum. Let me define F hat, which is the span of VI n times V hat bar J of the same level. So this consists of all scalar fields, all spinless fields, with derivatives ignored. Okay, and so I'm brave enough to write down with this general combination. I I mean this object here is a local field built from T and T-bar of a spin 0 and scale dimension equal to 2m. Okay, so it's a large scale dimension, generally large scale dimension thing. So what I want to consider, at least formally, and in much sense, actually, is an expression, is something like action with conformal field theory perturbed by generic vector out of this space. Well, I mean, there's some convergence needed, but whatever. And it turns out that in classical, at least in classical mechanics, this makes perfect sense and can be really analyzed. D2x. Okay, I'm going to write down. Sigma is sort of an element of this space. All right. So we can write it down. Sigma of x. I'm prepared to write it down explicitly. Well, not explicitly really. Sum from n equals to 2 to infinity. Sum over I and j for each n. Alpha ij n times vi n vj bar n of x d2x. So it is determined by infinitely many coefficients. All right. So T-Tbar?
Yes.
T-Tbar is just first term. When I substitute n equals to 2, then each of the spaces v2 and these are hats. No, it's a basis vector. The basis in this space v hat is the space is one dimensional. It's furnished by T, and this one is furnished by T-bar. So what we have is T-Tbar here. So, but I'm adding all this collection of all these terms in preparation to see how this bends when you go along the T-Tbar flow, for instance. Or, in fact, we will be able to analyze generic situation in this context. All right. So that's the action. These coefficients, of course, carry dimension. The greater n, the greater the dimension. So it's convenient to isolate overall dimensional factor, which is alpha to, which I denote alpha to n minus 1 times beta ij n, where these are dimensionless. And alpha has a dimension of mass to the minus 2 or length square or whatever you prefer. So then my my sigma becomes some expression of this sort, which I at the risk of being boring, I will write few first terms. So sigma is some series of this sort. And it's alpha T-Tbar of x plus alpha cubed beta 1, 1, 4, something like that. So to match notations. T squared, T-bar squared of x. And then there are the higher levels have multiplicities. So it's going to have to be alpha 5 to something like B116 T cubed, T-bar cubed plus B126 T cubed, T-bar prime squared, and there is other terms, similar terms. So there are 4 terms to figure out. And then there are higher order terms and so forth. So this is expression in which all these composite fields are taken just from conformal field theory. So these guys, T and T-bar, are conformal field theory. So this is complicated expression in terms of energy momentum tensor. You can write yourself Hamiltonian associated with that and so forth. It is generally a very difficult thing, right? Because it's unrenormalizable. If you start to treat it as a quantum field theory, you will have all these problems which I mentioned before with this, counter terms and dependence of physics, general dependence of physics of the subtraction scheme. All right. So it's an unrenormalizable and not defining. The expression for the action needs to be supplemented by generally infinitely many conditions defining subtraction scheme. That's where it's still possible to do that within this theory, because just here the fact that the space F naught, a vacuum space, is closed with respect to operator product expansions is crucial.
Sorry, why do you consider VIN, VJN, both N?
Why did I consider that? I wanted to, I don't know why, but I did. I wanted to first isolate scalar components, and that makes it necessary to marry level n from the left to the level n from the right. And then it makes natural gradation of the whole series in terms of dimensions. And so I'm easily, now once I have taken taken this precaution about decomposing, the isolating overall scale dependence went smoothly. All right. Otherwise, I would have to do a lot of hand waving. All right. Anyways, in principle, I believe one can develop this perturbation theory in alpha, and then let's say if we are interested in something like T-Tbar flow, one can order by order define yourself at each order energy momentum tensor, something which satisfies continuity equation, and it's independently of implementation of cutoff procedure, you would have a field which satisfies continuity equation as long as distances concerned are much larger than the cutoff distance, and then you can take it as an energy momentum tensor at each order, and then you say that your the derivative of this object over alpha is going to be equal to T-Tbar computed in this L order and so forth, and this supplies infinitely many conditions, which basically, I believe, would fix the subtraction scheme. So in principle, this is, I think, in principle doable. It's very little known about this series beyond the leading order. So it's open problem, and I believe in the way to the solution of the problem. One will discover a lot of miracles about this particular perturbation, like miraculous constellations of some divergences and so forth. But this is generally open problem. Take it as an advertisement. All right. So defining it, let's say, as a T-Bar flow or something more general, if you wish, can be used to fix the scheme and then follow the flow. Now, next, of course, the whole thing becomes infinitely more simple if I take also the classical limit. What it implies is that now all these divergences which come from fluctuations are suppressed by powers of C, and in the leading order in semi-classical approximation, well, I don't know, but it looks like they may be ignored. And therefore, it's the action of this sort defines the classical theory. Okay, and we are going to deal with this classical theory. So once this is a classical field, so we have T and T-bar classical fields, which is the same. All these composites which enter here are also classical field, and basically what we are going to do is to extremize certain complicated functional. All right. So T and T-bar, the solutions to any expectation value would be determined by some classical configuration of T and T-bar, which extremize perhaps certain effective action. And actually, the thing becomes dramatically simpler if I concentrate first attention on this problem of ground state energy on a circle. Okay? Because now I have let me draw this annoying picture again. So I have a cylinder, and I want basically a partition function on this cylinder, of the theory on this cylinder, which is determined by its ground state, by the ground state. So I have a x here, y here, in finite circumference. And so, I mean, it's natural to assume, although it's something which is I'm not very 100% certain about, but it's natural to assume for the first run that the associated classical solution associated with ground state respect all the symmetries of the problem. So there is a translation symmetry in all directions. So the classical solution and similar to T-bar classical of X are some constant configurations. Okay. This actually this assumption is supported by the result. Will be supported by the result. But that makes a dramatic simplification, right? Because all these objects C sub I are essentially polynomials. These basic vectors V sub I n are, let me call 2n, because otherwise it's a little bit different structure. But it's t to the n plus t to the n minus 1. Well, sorry, n minus 2, n minus, I already forgot. T to the n minus, minus 3 t prime squared plus terms like this with some coefficients. Okay. Anyways, it involves derivatives. beyond the first term, it involves derivatives, and because it's classical field and the classical configuration is constant, we are going to throw these things away. All right, and so all this Vi to n, I mean, for odd n, they simply are small, become small, 0, and V to n becomes T to the n, and as a result, this sigma becomes a function of a single variable. All right, this out of this Vi, Vj, only the leading terms survive, and then sigma sub alpha, not psi sub alpha of x, is just alpha T-Tbar plus alpha cubed with some coefficient T-Tbar squared plus higher powers. Basically, it sums to some function which I denote 1 over pi alpha u of alpha squared T-Tbar. Okay, so it's given by a single function of this T-Tbar. So we arrived at this problem with the action. Let me write it down because I'm going to refer to it again. And again, we are arrived at this action under this assumption that the derivatives don't matter. So I will, for a long time, I will consider the action which is ACFT plus integral 1 over alpha pi alpha u of alpha squared T-Tbar over x.
What happened to beta?
They become a coefficients in the Taylor expansion of this function. There was a lot of betas because a lot of terms become zeros. There is, for each level, there is one independent coefficient, and they are absorbed into a single function. Is it clear?
Yes, I don't just think it's written.
No, it's not written. It's a kind of. All right, so let me write it. U of x is some certain beta to n, x to the n, and these are remaining betas. Okay. So the theory, the classical theory. I mean, I thrown this away at this derivatives. I mean, specifically for this problem of ground state energy, but I believe as a classical field theory, this is fine, even for any theory. It's not that generally. All right. So I trust there is some approximation in generic classical theory in which you could ignore these derivatives, but I just in general I don't know what parameter controls this approximation.
Why is there 1 over alpha?
Because I want to furnish dimensions. All right, this is integrated over d2x, and I need to make something dimensionless for the action. Remember, action is dimensionless, so 1 over alpha is exactly 1 over length squared, and this is also a dimensionless argument. Okay, now before moving forward, let me something happened. All right, so let me transform it a little bit, introducing auxiliary field, which is, I mean, everyone would advise me to do at this point, right? So I define myself a prime, which depends on auxiliary parameters mu and mu bar, and this is going to be ACFT plus integral 1 over pi integral T mu plus T bar. So I introduce additional auxiliary field. Everyone does this gazillions of times. And so I have minus 1 over alpha W of mu bar. So this W is another function of its arguments, and it is just the double Legendre transform of U. All right? no, it's double. Well, okay, Legendre transform of U of alpha squared T-Tbar in both T and T-bar. So in two variables, right? So not in the argument, but in both variables. So this mu on classical on extrema, this mu is related to T by this equation. Extremum equation equal to 0, which leads to some relation of the type mu equals to alpha T bar times some function g of mu bar, and mu bar equals to alpha T g of alpha of g of alpha squared T bar alpha squared T-Bar, where this alpha squared, this g is related. So you basically get something like T alpha T equals to mu bar W prime of mu bar, and similarly for T-Bar. And then you invert this relation to something like this. All right, and in fact, it's not difficult to relate G to U because it's the dual nature of the Legendre transform. G is simply U prime of X. If it's not clear, I do it as an exercise. All right, so this now defines this whole action now defines a certain classical field theory, and I actually have a number of interesting things to say about this field theory, classical field theory, not limited to the case where the solutions are constants. All right, but I mean the rough statement is that one can write down explicitly very nice equations of motion in closed form, and even action and the action is even local in terms of solutions of Beltrami equation. So if you have some configuration mu, you define yourself a function f of z and z bar, which solves the Beltrami equation. Okay, this is Beltrami equation. And the action is getting local. Polyakov noticed that many years ago that there is a local action in this variables. But I don't want to waste time because I have a lot of other things to say. And let me just proceed with the assumption that mu is constant, in which case, of course, the Beltrami equation is easily solved. So let me now, when I took full advantages of these assumptions, let me define the full functional, which I am going to extremize. This is some functional of mu and mu bar, and then there is a minus 1 over alpha pi integral minus 1 over w of mu bar over x, and the integral is over cylinder. So this integration is trivial. Just brings up the size of the area of the cylinder, where L is the large length of the cylinder. And the functional h is just a generating function for the for the correlation functions in conformal field theory. So it's by definition, its expectation value e to the minus 1 over pi mu t plus mu bar t bar over x, and the expectation value is taken over CFT. So you bring down this energy momentum tensors and integrate and do all these calculations. I am not going to write down formulas. That's all right. So now, of course, because T and T bar don't talk to each other, up to contact terms, this H is a sum of contributions of left and right. So H of mu and mu bar is F of mu plus F of mu bar plus where each of these F's is complicated non-local functional, but one can have a local contributions which in this case of constant mu and mu bar just contribute additional terms to this function W, which is at this point arbitrary anyway. So this doesn't the count of contact term doesn't change much. Well, I cheated a little bit here, but not really to change the conclusion. All right, so now one can write down equations of motion and so forth. It's essentially the statement that well, I mean, evaluate this F on the constant fields, which can be done really without calculation, just doing these things with your hands, because the statement is that if you go to this, make a transformation from Z and Z bar to this F and F bar, this quasi-conformal map or some sort of general coordinate transformation, this accounts for this terms even for finite mu, and then this transformation for constant mu is just a generic affine transformation, which basically takes your cylinder, dilates in this direction or in that direction, and then it changes the r, the radius of the cylinder, by some factor, and the Euclidean time by some factor. You find that F is, I actually already forgot this. In this case, F is because there is some sort of additive term which I always forget. So it's L times R, which is the size of the cylinder, and then it is multiplied by pi c over 6R. That's essentially the ground state energy of the minus pi c over well, minus is already here, so pi c over R, and then there is a factor 1 plus 1 over 1 plus mu minus a half. Or maybe more instructive way to write it is in the form LR times pi c over 6R, and then 12R, and then there is 1 minus mu, 1 plus mu, and that's the factors with which you dilated this or that way.
Here we assume that you're just taking the vacuum contribution?
What's that?
Just the contribution from the vacuum. So
Yes.
you're taking L to be very large?
Right. That's what I'm after, the vacuum energy.
Yeah.
All right, so I wrote it in the form prepared to neglect its constant term because it's not important actually. So we are arriving at mathematical problem of extremizing the effective action, which looks like this. I call this E of mu and mu bar, and it has the form minus pi I strip it from large R factor by C over 6R, 1 plus 1 plus mu, plus 1 plus mu bar, minus 1 over alpha W of mu and mu times mu bar. All right, so this is already, no, this is a factor of this. Well, there is actually minus 1 to be precise, and then there is additional factor of this sort. All right? No, wait, there is R factor because is there R factor? Yes, there is R factor. I cannot remember where it came from. All right, anyways, that's something to extremize, and it's maybe instructive to look at this expression from general point of view. All right, we have two terms. One, of course, this one dominates at large R or at small alpha, and it better be positive defined. All right, if we want a Euclidean field theory to make sense, it better be positive defined. Then there is this term which dominates at small distances, and this term is dangerous, right? Because see, this one depends on mu bar, absolute value of mu. So it changes with the absolute value, only with the absolute value of mu. This one depends on imaginary and real part of mu, and if you manage to squeeze yourself close to these poles, it has a danger in the mu plane. It has a dangerous point -1. This is complex mu. Plane 0 is 0 sitting here. So if your field configuration sneaks to the vicinity of this point, you can make yourself functional as negative as you wish. This basically is effectively shrinking the closely related to tachyon effect. All right. So the way to kind of to try to avoid that is to isolate, to put a wall. That's a business of the day. Put the wall. Let's say I take as an example of this phenomenon, I take -1 over alpha, which gives W of mu bar, okay, to be, let's say, a pole, okay, like 1 over -1 over alpha W of mu bar be 1 over absolute value of alpha times, let's say, to be concrete, let me say 1 over rho squared minus mu bar. All right, then you have a sort of infinity along the circle of the radius r, and if rho is smaller than 1, it's sort of, I mean, no one jumps to fall into this dangerous place. And so there is a totality of field theories, which in this approximation, which are stable from UV. And I mean, strange thing which I don't understand yet consists of the fact that if I assume something like that and calculate myself a ground state energy, it has this CFT behavior, ultraviolet, with some central charge which is inherited from all this structure. But it's definitely something larger than the original central charge. So that something goes counterintuitive to what I said at the one of the previous lectures, that attempts to follow it looks like a generic in classical approximation, generic flow, attempt to flow to UV would bring you to something pathological. Maybe this is just a form of the ground state energy, which looks fine, but there is other pathology here. That I have it's still not clear to me. it's in the process of moving the whole thing. And now let's talk about T-Tbar flow. Okay, now I can write down myself I have to skip a little bit of technique, but I can derive energy momentum tensor.
A W that has that wall, what does that imply for you?
Some nonsense. I don't know. It's you can solve it. It's smooth function which does something like this. Well, grows some way. I don't know. I really didn't pay much attention to how it grows because at this point I don't know what I learned from it.
I probably misunderstood. You said that something about the high energy behavior of this field?
Small radius.
R going to 0. Radius going to 0.
So there are many assumptions here that only you're allowed to look at only the homogeneous state.
Right.
Completely clear.
I agree. I agree, and it's of course very tempting to look at the fluctuations, which is also, I mean, open problem. But let me finish and see where it brings us. This kind of approximation, and it's now time to ask what the T-Tbar flow is, and without any comment, I will just tell you what it is. So W T-Tbar flow of mu bar is mu bar divided by 1 minus mu bar. So it's exactly where this radius hits -1. And so basically it's safe in every direction except for this dangerous point. And so let me explain. For sufficiently large R, when this term dominates, this is still a barrier, and you cannot jump over it. But when R goes to become smaller and smaller, eventually this term starts to dominate, and the field configuration can potentially leak through this point. I don't know how it happens. The fluctuational theory of this phenomenon is something interesting, but at least it must explain the square root nature of the singularity if it's behind it, because generally we expect, if we have a instability developing like this, we expect from physics some metastability, nucleational decay, complicated singularity of the Langer's type, and we don't see anything like that here.
If you actually solve the problem exactly for the ground state energy,
Yes.
you do see something that looks like a conformal field theory at high energies if you go through the branch path.
No.
Because it goes like linear and then linear again.
No, but do you mean the analytic continuation to
Yes,
small?
the continuation of the vacuum energy. It does look like a CFT at high energy.
No, there is no pole at 0. What do you mean?
There is this vacuum energy curve.
Vacuum energy curve. The vacuum energy curve, but we are looking at the singularity at small r.
Right, but what it wants to do, it wants to avoid small r.
It wants to avoid small r, but I want to see what happens if I just put it at smaller r.
Okay.
All right. My analytic continuation returns complex values. So my idea of what happens is that it becomes unstable, and this is a resonance state, okay, quasi-stationary state. And just what I said is that when quasi-stationary state like that develops beyond the mean field theory, one expects complicated singularity, while there is none. Okay, so that's the puzzle which I brought up. All right, so I'm sorry, but anyways, this returns of course the correct value, correct expression for the ground state energy and so forth. So it looks like, I mean, the problem of this curve, which I brought up before, this one, which Zohar rightly remembered, that there is a square root and the complex values beyond that is at least vaguely related to the loss of the ground state at short distances. All right, finally, any questions? Because I want to turn to something else entirely. All right, so now I have to be simply declarative. Okay, what I want to say, and why I wanted to say it, is that, I mean, there is a common wisdom developing that this kind of ultraviolet problems are closely related to this S-matrix problem, the very fast growth of the scattering phases with energy. And I want to argue against. Okay, and to do that, I would consider extension of this notion of T-Tbar flow to infinite dimensional flow, which emerges when you have integrable field theory as undeformed theory. To argue that, I will simply state, which I think I cannot remember if I made this statement already, but let me, if I did, I apologize for being repetitive. So that this kind of deformation is available, at least formally, every time you have a pair of conserved cards. All right. So the whole activity which I developed at the first hour is guaranteed if you have let me call them A mu and B mu, two fields, local fields, which both satisfy continuity equation. All right. Then if I form the combination A mu of x, B mu of x prime, then from this B nu, E mu nu, antisymmetric combination, then I have a one term which I call A wedge B of x prime, one term with the coefficient 1 plus derivatives. All right, so I can try to play the same games same games with different physical implications, of course, but you can play infinitely many such games if you have infinitely many integrals of motion. In integrable quantum field theory is furnished by an infinite number of integrals of motion, which I denote Q sub S, which is integral J mu sub S of x, E mu lambda dx lambda over some contour, and S represents the spin, but generally this J is a reducible, not a reducible, some tensor of the sort with S indices, which cannot be simplified on the pair of any, which basically is symmetric with all these indices, and in 2 dimensions it implies that there are 2 components, J mu sub S and J mu sub minus S, with all plus here and minus here. All right, so there are 2 components, and if one wants a scalars, one has to form these combinations, which I call x sub S, which is j sub s, wedge j s minus s, and then this spins plus and minus cancel each other, and we have a scalar. So there are infinitely many of this x sub s, and it's possible to show that if you deform your action adding these terms as a deformations, then the resulting theory preserves all the integrals. So you could consistently do this deformation remaining within, in other words, this sub x sub s are within tangent space to the integrable at given field theory, to the subspace of spanned by swept by integrable field theories inside the whole theory space. All right, and in fact, there are infinitely many parameters in this flow, and up to probably finite or at least much more comfortable codimension, it seems like almost filling this flow, almost filling the space of integrable field theories. I will argue that on the basis of well, something which is not really proven, but conjectured and checked in a number of examples, and that is that concerns the deformation of associated factorizable S matrix. Okay, so once I add this, the integrable quantum field theory, if it is massive, is characterized by factorizable S matrix. So it's a, let me remove this. So integrable quantum field theory, which is, I say, is massive. I assume is massive. Then it's leads to factorizable S matrix. Which is, I mean, the generic matrix element. I mean, there is only elastic process as well. I won't go into the details, but everything is expressed in terms of S 2-to-2 elastic amplitude, which in fact is a function of single parameter, which is theta 1 minus theta 2 rapidities of the particles to scatter. All right, there are some general conditions on this amplitude. It can have flavor indices and all, and there are conditions like Yang-Baxter equations, unitarity, plus analyticity, and crossing. But once you satisfy all these conditions, you are still left with ambiguity, which is known as so-called CDD ambiguity, CDD factor. So you could take a solution to this equation as 2-to-2 of theta and replace it by and multiply it by any factor phi of theta, the CDD factor, where y essentially is 2 pi I periodic function. Phi of theta equals to phi of I pi minus theta. That's from crossing symmetry, and 1 over phi of minus theta. That's from unitarity. So there are infinite space of factors, some nonlinear space of factors of this sort, and this e to the which we
What is the analytic structure of this?
it's going to be meromorphic function.
It's known to be meromorphic.
Meromorphic function with some limitation on the position of poles. You don't want to have a complex poles on the physical.
For example, to have infinite number of
You are allowed to have infinite number
then
of
you
poles.
make some essential
You can add infinitely many poles, which would accumulate towards infinity, or accumulate towards your favorite point in the complex plane. So you could do whatever. It's analytic function with some rather mild from the general point of view analytic limitations. All right. Hopefully I will say something about what I am preparing here. Anyways, this dressing factor which we discovered in the T-Tbar flow was a phi of theta equal to minus I alpha hyperbolic sine of theta. All right, and you could check that it satisfies all these requirements. Now it is conjectured, and it, just like I said, check it in a number of examples, that if you add a combination of this delta alpha sub s with x sub s, right, integral, then the scattering phase changes, phi becomes e to the exponential of minus I alpha sub s hyperbolic sine of s sub theta, s times theta. All right, so it grows even faster.
S is the spin.
S is its spin, yes.
Maybe there is a mismatch. For spin 2, you want to recover T-Tbar?
For me, T-Tbar is spin 1 because it's Lorentz momentum. It's a spin of charge, because my current is J mu sub s. This one has s plus 1 spin. Sorry, I had to clarify that. So this looks a lot more disastrous than the T-Tbar flow, but I didn't write any coefficients in front of that because I didn't care to normalize anyway the field's excess. So you could make basically these coefficients move. But anyways, this is now infinite series over S, and as a result, it could very well converge to something which behaves very decently, being analytically continued, behaves. So this can be a power series decomposition or Fourier decomposition of a function which can have a finite singularities, but behave very decently at infinity. So typical situation, you add several resonance poles consistent with crossing and unitarity and everything, and then these poles do not spoil the ultraviolet behavior. Just I mean, in the scattering phase, it would have in the derivative of the scattering phase, you would have a bump at certain energy, which would mean that you have a, I mean, more dense space of states near this energy and so forth. And so generally, if you put them in right place, you are increasing the density of states, generally speaking, by doing so. I mean, increasing if you have a appropriate sign of this alpha. But then you need to keep the poles away from the physical sheet and so forth. So you generally are increasing the density of state. And of course now it's once you have a S matrix, so you have alternative representation of this factor, which is a product of sine theta minus IB P divided by sine theta plus IB P, where instead of collection of a product of some P, instead of collection of this infinite collection of these numbers alpha sub S, I have positions of poles, and I have this nested space where I add more and more poles and so forth. Now, the activity which one immediately is compelled to develop is to compute because there is a machinery to compute ground state energy given as matrix. I don't want to explain it because I'm out of time, I'm afraid, but it's some sort of black box where you push in the scattering matrix and pull out the ground state energy, at least numerically. All right, it's some integral equation which you start cranking like mad numerically and produce yourself these curves like what you have for the ground state energy is the function of R. And when I prepared to do that, I remembered that we have already done that. And some like 30 years ago, when Alyosha discovered the staircase model, we were very encouraged. We thought that now we throw more. In fact, the staircase model was the first simplest example of this exercise, and it was very rich in content, although it gave something very consistent with local physics. But if you start throwing more poles, you keep ending up with singularity at finite R. So a typical behavior with the CBA equation, if you are not adjusting these poles very carefully, not fine-tuning them to very special values, it is developing something like this. So again, if I look at this ground state energy as a function of R, I would have again something like this, and then it would turn to reproduce maybe something similar, but then it would develop a certain finite size, which I call R star, which would develop singularity. And moreover, Alyosha did very careful calculation near this point, and it was always square root. So that rings the bell. So it looks like it might be similar. But first of all, now the problem doesn't seem to be related to scattering amplitude at high energies, but related to something else. There is some potential instability behind the theory defined by basically generic S matrix. And so the lesson, I don't know how it goes for four-dimensional space, but the lesson for integrable field theories is that if you take yourself arbitrary factorizable S matrices, with generic collection of resonance poles and stuff, everything is positive, everything is unitary, all crossing symmetry is satisfied, and you count yourself a density of states, it's going to develop Hagedorn behavior.
What do you mean generic? By generic you mean arbitrary?
Yeah, arbitrary B constrained by inequalities, not equations, but inequalities. These B's are supposed to satisfy certain inequalities like being smaller than 1 in the absolute value and so forth. No, actually, even this is not true. They can be greater than 1.
So, Sasha, can you repeat? So you said it's not related to the high energy behavior, but
Because this goes to 1.
no, that I understand. But it's related to what?
The mechanism of that, the mechanism of that is not well understood. At least I didn't understand it. It's still beyond my pay grade. So but mathematically it looks like this. You plug it in the pole like this, all right, and then you have of course a bump in the density of states near this energy, but then somehow this bump keeps repeating itself at logarithmic multiples of this. I mean, it was in logarithmic scale equidistantly at higher and higher energies. And the bump becomes larger and larger, and And
How do you know that it's not related to the high energy behavior? I didn't get that point.
It goes to just
No.
take this formula.
because
No,
this
I-
one,
That's true. But that's the exponential. We're talking about the logarithm. How do you know that it's not related to the phase going to infinity?
because I can have just two factors of this kind.
Oh, you just have a concrete example. Where you
Right,
say-
I mean, I don't need infinitely many
Yeah, yeah, okay.
terms
Concrete
here.
example.
I take two poles like this, then the phase has two steps,
And that's it. Yeah.
and that's it. Yeah, and then, I mean, it's because each of the steps has a tendency to multiply.
Right. I see.
Just this is the same similar mechanism was behind the staircase model. So you had one bump, but it was brought periodically in logarithmic scale, and that would create all this staircase.
Then
But-
you do have like infinitely many new particles and some weird high energy behavior because you have this kind of logarithmic repetition of the resonances.
No, you don't have it. If you look at the scattering matrix,
Yeah.
it is just has one pole
Okay.
or two poles. There is just in staircase model there is just one additional resonance state in the scattering matrix. Here, I mean, you add two, and you have this property. There are cases where you take these B's, two B's, adjust them very properly, and you have then flow between two non-unitary some staircase between non-unitary minimal models.
This is some kind of bad news to the people who do numerical bootstrap because they don't put this condition in.
Which condition?
I mean, people who do numerical bootstrap just search for S matrices that satisfy unitarity and electricity at crossing.
Right, but they are aware of CDD ambiguity.
Yeah, but that means that many of the solutions that they find, many of these boundaries could be unphysical.
But all of these solutions are unphysical. Well, I mean, besides the solutions which we already know from integrable field theory, all of these solutions violate some principles one way or another.
You mean all CDD except finite two?
Yes, yes, which sort of complies with the intuition that
The finite two are just what?
So these guys would say those are the only variables, right?
No, what they're doing is that they do not look for integrable quantum field theory.
I know.
But what you're saying means that there is something missing in this list of conditions because already for integrable quantum field theories, clearly that's not enough.
That's exactly what I'm trying to say.
Yeah, so that means that, I mean, many of the solutions that they find which are not integrable quantum field theories could be unphysical, even though the S matrix.
They are unphysical well before this kind of this kind of problem kicks in, and they are aware of it. All right. Anyways, here is the situation. I think I made at least I worked hard to make myself clear, and that basically means this sort of complies with expectation which I tried to bring from the normalization group, that if you take some local looking physics and try to bring it to UV scales, that's this Wilson's argument, RG, blah blah blah, tells you that you are bound in majority of cases, in bulk of the cases, you are bound to develop some sort of problem.
Experiments might say, I measured the S matrix. I
Yeah,
don't care
so
about the
there is
density.
something that we're missing.
Right,
I
but
don't care
then
about
you
the
need to say, all right, that means something must substitute local physics, substitute for local physics.
That means that we're missing something about the S matrix.
Either I mean, it's probably both ways of looking at it are correct. Either you say we need to supplement something to the constraints on the S matrix which guarantee existence of local physics,
Exactly.
or you can say, as David proposes, say forget about local physics. Let's substitute something else and call it quasi-local physics, or gravity, or string. Well, I knew you are coming to that. I tried to avoid that, but all right. Anyways, that's the situation, and thank you.